Continuing with the problem, the electric circuit that was then under causal, we added a virtual C element to the zero junction. That did the trick. Another option was to use inertances, virtual inertances. Then you had to use two, one on each of the one junctions. That will also work. Now, the system has been causal. Let's try to get it. Here we have an effort 0, which is known. The flow we don't care about. We have a C element with the proper causal stroke, the integral stroke. And then we have this virtual thing. What will he have? A C element should have a Q dot here on the flow side. This one will have a 0. He's virtual. He shouldn't produce another differential equation. So I put a 0 here, even with a circle around it. But on the other side, I'm going to need an effort. It is not real, it's virtual, but I'm going to need him to be able to do the algebra to find the equation. So there I just add a virtual effort, E virtual. Now let us try to continue. Can we get anywhere here with these resistances here? What's the flow here? Well, I don't have it, and I can hardly get it. The flow here, don't have it, can't really get it. So we have to start with the zero junction here. Common effort. Who decides the effort? Well, that's where we have the stroke. That's this E virtual. So he is all over the place here. There you can start. And now we know the effort. We can find the flow. That will be E effort divided by R3. So we have the flow there as well. Now for the other two resistances, they are missing both flow and the effort. Well, but now for both of them you have an effort on each side, here and here, meaning you can find the effort hitting these resistances. So effort in equals what comes out. So the effort here has to be E0 minus the virtual. Then the flow on the other side, just divide by R1. And the same goes here. You find the effort, EV minus Q over C. And the flow, the effort, divided by resistance R2. This flow we will find here as well, even here if you like. And this flow, that's the common flow for this one junction. You will find it here, and you find it here. My first equation. Q dot equals this expression, E virtual minus Q over C divided by R2. So that's my first equation. What about the rest here? I mean, I'm missing something, don't I? It's just a first order system. I only have one energy storage element. So yes, I have found one equation for him, but this equation involves something virtual, something actually unknown. So I need another equation. Now, what have we used? If you look at the junction and the summation rules, well, I have already used the summation rule around this one junction. I summed the efforts to find this one. And for this one junction, already used the summation rule to find this effort. I have not used the summation rule around him. Okay, summation of flows has to be 0. So what comes in? This one. That should now read E0 minus EV over R1. He comes in equals what goes out. And what goes out? Well, I have a flow here. E virtual over R3. I have a flow going out here. Well, here's 0. I just write him anyway, just for cosmetic reasons. And then I have the final flow here, which is this expression, EV minus Q over C divided by R2. So there you find your equation system. A Daae system, differential and algebraic equation system, first order. Of course, you can do the algebra if you want. From this equation, you isolate EV equal to and insert this one inside here. Your choice, how you want to program this one. Any questions to that one? So, under causal systems, introducing this virtual element will give you a little bit additional work, solving an additional algebraic equation. That's all. That's all. You can do the same problem now with these two virtual I elements on the one junctions, not this C, virtual C. And then do the same, and you should get the identical equation. So if you are bored this weekend, then you can see if you can solve it. More examples. Let's see, down here I have a flow source on a point that hits a spring, that hits a mass M1. He's sliding one wheels, no friction. And here I now have a rod, something like this, stiff rod. He can tilt around this point, and up here I add another mass, M number 2, also sliding or rolling without friction. And then finally I have a damper and a solid wall. Find the state equation for this problem. Here I have a spring C, I have a damper, an R element, inertance 2, inertance 1. So how to solve that one? Well, this long stiff arm is then of course going to rotate around this point. But I treat the motion for the two masses as linear. So if the angle is not too large, then that should be okay. So physically here, actually what we have is translatoric motion hitting something now that rotates. That means jumping into another energy domain, and from this rotational motion up here you go back to the translatoric. So we need two transformers or two gyrators to describe this. But since this rod here, he doesn't have any mass, then we can actually just use him as a simple transformer, coupling the motion down here to the motion up here. And of course that one will depend on the distances. What do we have here? L1 and L2. Length 1 and here length 2. Of course, if they are equal, then you have no transformer at all. Well, except a positive velocity here will be a negative velocity up here. That's all. But if they are different, okay, then of course we will have some change there. Now let's have a look at that rod. If we just draw it here somewhere, like that. L1, L2. So now it's the question, the distance down here coupled with the distance up here. So if I now call this one y number 1 and this one y number 2, then you will have the following coupling between them. Y1 divided by L1. This angle equals this angle, Y2 by L2. That must be sort of given. This also means if you are not looking now at distances, but you are looking at velocities, just take the time derivative of this equation. What do you get? The velocity is coupled with the velocity. Yes, clearly this is a transformer. So let us now try to draw a bond graph for this problem. Starting to the left, down here I have a flow source. So that should read something like this. Hitting, actually it hits a one junction first, this point, or this point if you like, but this point has no mass, so this one junction is going to disappear anyway. Insert a spring, that's the 0 junction. Continuing, we hit mass number 1. Continuing, we go through a transformer. And on the other side, we hit a one junction with mass. And continuing, we hit a damper. And finally, we hit a one junction, which is a solid wall. So there we have it. What's the value of this T modulus of this one? What's the value of it? Well, now I went from down here to up here. So I know, say, the velocity here. What's then the velocity on the other side? Well, for this equation here, you can rewrite this as velocity 2 equals velocity 1. And then you have to multiply with L2 divided by L1, which then is the T directly. You know the flow here, flow on the other side is the first flow multiplied with T. So my transformer has this value. Okay, can we simplify here a little bit now? Yes, this one junction disappears. Here, this bond will disappear. He has 0 power. Then the 0 junction has only 2 bond. He also disappears. So we simplify the bond graph to the following. SF hits a 0 junction with a C element, continuing to have 1 junction, I1, continuing transformer, hitting a 1 junction with mass number 2 and a resistance. There we have it. Everybody with me so far? Okay. So now I remove this the physical problem. We don't need it anymore. And I don't need this one either. Okay, let's try causal strokes for this one. Start with the sources. Flow source has to be like that. That doesn't dictate anything, so we continue. I have a C element here. I choose integral for him. Aha, then this 0 is happy. He has found the 1 towards him. Then the last stroke has to be away from him. That doesn't dictate anything. But I have a mass here, so I choose integral for him. Aha, then the 1 dictates final stroke here. The transformer doesn't change anything. Stroke there. But then the last 1 junction has got the 1 stroke away from him already. Hence, the 2 final stroke has to be like this. Okay, so this is a differential stroke for the inertance number 2. So this is then what we call an over-causal system. And if you think about it, of course, these 2 masses are directly coupled. If you know the motion on one of them, then the other one was given directly with the transformer. So no, you should not get 2 differential equations for these 2 masses. They are directly linked. And if you had chosen differently, chosen the integral for mass number 2, that's up to you. You could have chosen that one first. Then what would have happened? You would have had a stroke here and a stroke here, dictating for the 1 junction. Aha, then it would have been differential on the other one. So the physics is covered. Either way you choose it, one of them will be on the differential form. Okay. So now let's try to annotate this graph. We had the source, x dot source was given. Don't care about the effort. The spring has the correct form, integral, so q dot and q divided by c. The first mass is on the integral form, so here I will have an equation p dot, and on the other side p divided by I, and here I have to be careful, I1. You could have used p1 dot as well, since you have 2 masses, just indicating this is the momentum for the first mass, not the second, so you don't get confused. But this is as far as you go with the sort of the thing that are given directly. So now we have to start nesting, finding the rest of the efforts and flows. Let's start here to the left. I have most efforts and flow there already. Starting here would be a real pain. So I start with the 0 here. Looks more promising. Common effort. Who dictates the effort? That's where you have the stroke. That's Q over C. Aha. So here I have the effort Q divided by C. And the cross also Q over C if you like. Okay, that's as far as he goes. What about the 1 junction here? Who decides the flow? That's where you are missing a stroke. So that will be P1 over I1. And here also P1 over I1. Then everything here is finished. I have a flow here hitting the transformer. What do you get on the other side? Multiply with T. P1 T divided by I1. And that flow actually dictates the flow for the last rightmost 1 junction here. So now you know the flow here. P1 T I1, and also up here P1 T divided by I1. And then you know the force here. Just multiply with resistance R. And the flow P1 T by I1. And then we are missing an effort here on the other side. And that was the differential trick. How to find it? Well, remember how it should have looked. It should have looked something like this, P dot P over I. But that was with a correct stroke. Now we go the other way around. So now we have the flow and then find the effort. And you have an expression here, how to find the P dot. Well, you multiply with I, then you have the P alone, and then you take the derivative. So here we will have derivative of the flow P1 T divided by I1 multiplied with I2. There we have it. Now I'm running out of space here. What then about the effort here and the effort here? Well, we have to find them somehow. I can find an effort here, A, by using the summation rule around this one junction. So the effort in equals the effort out. And this is 1. Now, if you do the derivation here, it's only P1 that gets a dot. The rest are constants, so you write it as P1 dot multiplied with T multiplied with I2 divided by I1. So that was the effort here, plus this effort, plus R P1 transformer over I1. And then if you have an effort called A here, what do you find on the other side of the transformer? You multiply with a T. So here you will have an effort A multiplied with T. And then we're done. Then we have everything. Now, what about our equations? Well, I have 2 junctions left. I haven't done the summation rule around yet. So we can start with this one. The sum of the flow has to be 0. So what comes in, that's x dot s equals what goes out. What do we have for flow? I have one here, a q dot. And then the flow down here, plus P1 over I1. So there I will have one equation for my q dot. And the final summation, sum all the efforts around this one junction and get 0. So the effort in, that was Q over C. He goes in, equals what comes out. Well, that has to be P1 dot, and then plus coefficient A there multiplied with T. So here I now have my 2 equations. Still not complete, is it? Because I have this A variable, which I have here. Yes, you can insert it, and then you see you get another P dot, P1 dot inside here as well. So let's try it and see what we get. Equals P1 dot plus A. It's already P1 dot multiplied with T square, and then the ratio I2, I1, and then R multiplied with P1 over I1 multiplied with a T and multiplied with a T again, since we had a T there. So here, if you now rewrite this equation, you have two terms with P1 dot inside. So that's the effect of this differential form. You will produce another of your dot variables, one place in addition to the original. So that's the only thing that's happening. But you see it will cost you a little bit of algebra. So if you want to write this one on the form P1 dot equal to, what will it be? Well, this term on the other side. So it should read something like this: Q over C minus R P1 over I1 T square divided by 1 plus, and then T square I2 by I1. There we have it. If you multiply with I1 on up and down here, you can rewrite it a little bit. You will have Q over C I1 minus R times P1 T square divided by I1 plus T square I2. Now what's beneath here should look a little bit familiar, shouldn't it? Let's go back to the problem. So you have a mass number 1 here, and then this rod, and then mass number 2 up here, and then he can tilt around some point here. So the motion then should be directly coupled with a transformer. And if the system was as simple as this, okay, then you had I1, transformer I2. And what was the possibility we had here from exercise 2? You could join a transformer and an inertance. And what was the expression? That was T square multiplied with I2. You could say this is now an equivalent inertance, sort of an inertance that is felt for the motion down here. And that is indeed what we have. So here you have a sort of an apparent mass looking from, say, the motion downstairs, down here. So if we only had the mass up here alone, we didn't have the damper, then yes, we could have simplified the entire system using this trick. The sad thing was that, okay, I had more than just the inertance on the other side. I had the damper as well. So we couldn't really do it. Here it would be possible actually to calculate everything using this virtual mass or equivalent mass, but rather tricky. Easier than just to do it the straightforward way here. Okay, any questions to this one? It's okay? Yep.
What if the rod had a mass?
What if the rod had a mass? Yes. What then? What then? normally we like this bond graph system because it should be easy to change the rules. Just add another element and then you sort of instantly see, okay, what will this affect my equations. But putting him into a mass as well. So now he's a rotating mass. So now we actually have to expand the problem quite a lot actually. So let's try. This was a C element and then a damper. And I had inertance 1, inertance 2, and here I now need some rotational mass. Call him J. And he rotates, the J then has to be calculated according to the rotational point, of course. What will the bond graph look like now? Well, flow source, and then a 0 to the C element, one junction for mass number 1. And now we have a transformer. Not the same transformer as we had the last time. This transformer, he will transform this motion into the rotational motion here, rotational speed. So here you will now have a bond junction with a phi dot, a rotational speed. And this one junction will have mass, J, and then another transformer, say T1 and T2, going finally back to the translatoric motion up here. Again, finding a 1, mass number 2, and the final resistance. So that will be the effect of adding a mass. Now let's see, this one junction here we can skip, but that's actually all we can do. Yep. So now let's try the causal strokes and see what kind of a problem do we have now. Anybody care to guess? What will the order of this system be? How many equations will I get? From the previous one, I got 2. I had one from the spring and one from the, say, combined mass. Will I get the same now?
Yeah, one more. So 3.
Well, let's see. Let's see. Flow source has to be like that. Then doesn't dictate anything. This C I choose here, okay, then he must be here. Okay, that doesn't dictate anything. Again, start choosing. I choose for I1, I choose integral up here, then he must be given here. Transformer claims must be given here. Aha, then for this one junction, both has to be towards the one junction, and this transformer now dictates has to be here, and then everything is given like this. So now I have 2 masses, both on the differential form. And again, since all 3 masses, they are directly coupled, if you know the motion of one of them, you know the motion of the 2 others as well. So it's still just a second order system. And you can play around with this if you like. You could have chosen any, the integral causal stroke here, for instance. Then the rest will be dictated to be differential and differential. Just try. So you see, it didn't change the dynamics in the problem at all. So just a little bit more complicated, but nothing with any additional differential equations. Of course, if you start playing around with the system like this, a spring and a spring, thank you very much. Now you are talking, what will it be? 1, 2, 3, 4, 5, 6 orders to system. That's 6 equations. Just try. Rather complex. Other questions? No? As I said yesterday, put in some effort on exercise number 4. It's very good training for handling bond graphs, and you will get very good solutions afterwards, where you have the solution then very step by step, the whole process from going from a physical problem down to finding the state equation. So do some effort with exercise 4. Okay, then we stop a little early today.